Okay.
Yeah, now it's going down.
Is it okay now?
I think so. Yeah.
Can you hear me? Checking.
Yes. Okay. Sorry about that.
So, my initial plan was a survey of Cartan subalgebras, but it would have been taken too far away, and there was no way, at all, to make this survey. So I will concentrate on something very old, which is, in fact, which initiated the study, in fact, which initiated my work, my thesis. That's the result by Neumann and more. Back to 1977. We exhibited the relation between Cartan subalgebras, infinite Neumann algebras, and countable measured equivalence relations. So that's the term that I'm going to describe to you. I'm not, I motivated the definition in the C-star algebra context. I'm much more familiar with C-star algebra than with von Neumann algebra. So I'll try my best, but I'm sure that experts will, I may make some mistakes. So the first definition, so M is a fundamental algebra, or I would say abstractly, I would speak of W star algebras. So is Cartan. So we say Cartan pair if A is a meson. So it's commutant in M is equal to A. A is regular. Now, something which plays a big role, in fact, that's probably the only interest, at least to maybe to some of you, is to put inverse stoic groups in the stage. So, in fact, there is only one inverse stoic group which occurs, which is here. So that's the normal. Sometimes I think it's called the groupoid normalized, which is a very bad word because it's not a groupoid. So I think I don't know what's a good word, but I call it the normalizing. So it's N of A. So that is the set of partial isometries of N, which normalize so you wanted to generate, so it means the linear span, because it's closed on the multiplication, the linear span is weakly dense in M. So it generates. In the situation of a cross-polar, it's something which automatically occurs. And the third condition is that there exists a faithful expectation, normal, Okay, that the definition, and the definition goes back, was not invented by then. It's the name of singular should be mentioned. And we also have Cartan subalgebras. Now, the Borel equivalence relation. So we say that an equivalence relation so I view it as I identify the conservation in this graph. So I view it as a subset of X plus X. So the Borel means that just that it's a Borel subset. And X is some Borel space that I'm going to specify later what it should be. With countable classes, equivalence classes. And we say that a measure mu on X is quasi-invariant. On the R. Now, R sits inside the product. So we have the two projections, but I don't call them pi 1 and pi 2. I call them range and source map. S. And the fibers are countable. That's my assumption. So I can lift my measure mu here. I just integrate along the fibers just by here, so the counting measures and integrate over mu. So I get two measures on R, which is S star mu and R star mu. And I will say that mu is quasi-invariant if R star mu is equivalent to star. And the theorem relates these two things. So I assume that this data and the theorem say that on one end, the Cartan pair is always of the form L infinity of X, W star of R, and there is a gadget which is a two-co cycle. So so I should add but sigma, so R2 it's a subset of X with value in the circle Borel and which satisfy these relations. Which I don't write because I don't do that. So it's a two-co cycle. That's what's here. And I didn't say what's the sixth algebra, the algebra here. It's just these are matrices. So you start, you define so you have functions from R to C. You just choose them so that the product of matrices can be defined. So just arithmetic matrices. So if the support is such that this sum is finite, so and of course you want x, y, and y, z to be in R. You want this sum to be finite, and you put the cosine term. And the adjoint what it should be. So that gives you a star algebra. In order to have a von Neumann algebra, you have to construct a representation, and the representation is just the regular representation. Regular representation on L2. And in order to be specific, you see here I didn't write the measures, but you have two equivalent measures, so you can choose one or the other, but it's convenient here to choose. And you define variable A of psi, just the convolution here. And the von Neumann algebra is just the von Neumann algebra of digital presentation. So so I explained everything here. You put some assumptions. Here you assume that L2 of the standard representation of M is separable. When you say that M is separable, that's the usual assumption. And here I'm assuming that X mu, the standard space. Standard measure space. You interrupt me if you
have questions. What does it mean, the equivalence of the two measures? It means
I'll just mean that they're the same null set.
okay.
So, and there is a gadget which comes out of that, of course, it's the random Koenig derivative. And in fact, that's it's very important gadget, and a byproduct of this modulo much work is that this so which is and it's one cocycle. It satisfies the Shy relation at the X level. So and so one. So it is an invariant of, in fact, it will be an of the equivalence relation, but it's an invariant of the von Neumann algebra itself. And when the von Neumann algebra is it's a hyperfinite factor, it's a complete invariant. And so there is a lot of information. Okay. Now, what do I have to say new about this? Okay, I want to put inverse semigroups into the picture. So I will go not to equivalence relation, but I will go from Cartan to inverse semigroup. Cartan bears. inverse semi-groups. So which I'll abbreviate by ISG. This is absolutely, you have it in front of the eyes as soon as you notice that the normalizer is should I recall what an inverse semigroup is?
I think so. Yeah. Yes.
So, it's groups people know, semigroups people know, and definition. S is a semigroup. S is an inverse semigroup if for any S in S there exists a T in S, so that S star, how do it go? ST star, star, yes, S equal S. It's in fact instead when you have a semigroup of isometries, then this is clear because T is the adjoint. So I mean ST STS equal STS equal S, and same thing with TS T. Is this right? And TST is equal to T. Yes, think in terms of the partial isometries. Okay, the set of partial isometries is not an inverse, it's not a semigroup. The product of two partial isometries is not partial isometry. The product of two projections is not a projection. But, and then, and I guess in the definition you put, you have to here, and then you write T equal X. So there are, in fact, two basic examples, semigroups of partial isometries. So you see, for instance, if you have a U, then the domain projection is U star U. So that doesn't do anything, you get U. And if you write the range projection, which is U star, you get U. And the second example that we are going to meet is pseudo groups of transformations. Just take a set X, and instead of looking at bijections of X into X, look at partial bijections. So just from on subsets. And you compose when you can compose. And then you will see that, and also, if you have a subset, you have the identity map. And we'll see that you are then the inverse is just if these are partial bijections, the star is the inverse. Okay, that's what and when you have a semi-group, you know, what's very important, what I call S0 or sometimes called PS. These are the idempotents. So they. Now, SS star and S star S are idempotents and they commute. So, and so you have two maps, and you just like in a, so. S. You can either have the domain, which is S star S, or the range, S star. This, with this definition, you see that this is an idempotent. This condition. And in the product here, you write E smaller than F if E is equal to a little game, you can check that the multiplication is commutative on the idempotents. So the idempotents form a commutative semigroup. And you have this, so that defines an order. And so you have an infimum or me, which is just the product. So that's what an inverse semigroup is. And just the partial isometries that I say with, if you have only partial isometries in a Hilbert space with commuting which are closed under involution and whose range and domain projections commute, then you get an inverse semigroup. And conversely, the necessary sufficient conditions for having an inverse semigroup of partial isometries. So if in the case, so here, so what here there is nothing much to prove, just the usual product and the usual involution make it, and here the star is the usual star. And moreover, so in fact, the whole proposition is different. One, as I say, the normalizer is an inverse semigroup. Second, its sets of idempotent is what I will call the A P. P for projections. So that's the set of projections in A. A is an abelian von Neumann algebra. So the projections. And okay, I'm going to use something like it's Neumann decomposition. So I will is the extension API. So these are the partial isometries. Okay. It is a sub-inverse semigroup of N of A. So I write an extension means an inclusion into N of A But not only that. The inversely group or groups, I'm going to say, you can act by conjugation. So API, in fact, that's from its very definition, API is invariant under conjugation by elements of the normalizer, that's the definition. So it is a normal sub-inverse solution. So you can take the quotient. And the quotient, in fact, is something which in fact, you see that you can view, you define a bit of notation. So U defines a star isomorphism which are what alpha U, not from all of A, but I have to take into account the domain. So A U star U into A U star. So A is sent to I conjugate U A U star. Now A is a commutative C-star algebra. It's a von Neumann algebra, but it's a commutative. Yes, commutative is not. It just appears in one. It's a maximum ability. It's ability. So I write it as a C of X. So if I introduce the spectrum of A, so that A will be identified to C of X, I will get a corresponding map on the space. So I call it phi UU, which will be, I have to take the transpose of alpha U star, which maps, you say UU star, I view it, it's a projection in A, and I view it as a Klopen subset of X, and which, so I call this the domain of U. So it's a Klopen subset of X. It's given by a projection. So it's a Klopen subset of X. And
Right, that's so the API there is the pathwise on in A.
yes.
But A is commutative, right? So
Yes.
So these are the projections, are
Yes, these are projections which I identify to a close Klopen subset of X.
Right. Okay. So the API and the API are the same.
No, API, no. It's a little subtle. It's not so subtle. That's API are partial isometries. So there are functions, you see, supported on Klopen sets with value in the circle.
Oh, okay.
That's so it's idempotents are the projections.
Okay.
So it's a commutative inverse semigroup. In fact, it's more like that. Technically, it is called a Clifford inverse semigroup. I refer to, for instance, Mark Lawson's book, and so it's also, it can be viewed as a sheaf of groups. In fact, T-valued functions. That's okay, but so that's you see, that's what I said. So the Neumann decomposition, because this is really G of A is just a set of these maps. So it's the second example that I gave, a pseudo group of transformations. So U belongs to N. So it's a pseudo group. And another name for that, it's called also fundamental. So it's for those like me who are more familiar with groupoids than inverse semigroups, they correspond to principal or topologically principal groupoids or equivalence relations. So that's fundamental. While this is called, sometimes it's called Clifford or sheaf of group, really correspond to a circle bundle, which is here. That's so that's and this should be called a twist. So that's the version inverse semigroup of a twist.
Say again the definition of this phi u.
It's just, you see, you've got a map from this algebra to this algebra. And the transpose, you let it act on the draw. So it's in the spaces. That's I don't think I need more to write more, otherwise. Okay, so I gave all the definition. So it's quite high. In fact, it's more than an inverse semigroup. So I go from Cartan pair to 2. And there are some more properties. Okay, and I forgot to say something. I forgot to say that all what I'm doing is done. It's not me. And I didn't mention. After the work of Danzig and the bits, that's called the fundamental algebras. And extensions of inverse semigroups. And it's published in the proceedings of the Edinburgh Math Society and 2006. Right. And also for this approach, you can. There is a book which is unfortunately not published by my colleague Neumann, Claire Nanterament, and Cyril Popa, which is called Introduction. They do the case of two instructors. It's available on Claire's website. It's okay. That's fine.
Can I also ask about this the problem term? So when you say this isomotic, I guess you mean a map from M.
No, that means whenever you've got whenever you've got the Cartan pair, you can realize M as the fundamental algebra of a measured equivalence relation.
But then can you say that this you have like a map from M, let's say M1 to M2 that maps the Cartan,
yes,
and commutes with the expectations and not normalized.
Yes, in fact, it's you've got a functor from category to another one.
Oh, okay.
Which preserves.
Thank you.
No, where am I? There are some more properties here in that situation that I record here. So definition N inverse semigroup G, just like G is called Cartan. That's if okay, the main features that we need is that it is fundamental. So it's fundamental means that it is a pseudogroup. So that means it's automatically an inverse semigroup acts on its idempotence. We saw an example. And being fundamental means that it acts faithfully on its idempotence. So it is a pseudogroup. And its units, its idempotence is a complete Boolean algebra. And third, if you have a family SI, which is orthogonal, so orthogonal here means, you use this, it's an inverse semigroup, so just means SI star Sj equals 0 for any I different from J. Then you can define a supremum. And when I say supremum, is that not only I define an order I defined an order on the set of idempotence, which is here. But the same definition defines an order on S. You will say that S is less than T if there exists an idempotent such that S is equal to TE. For instance, in the case of a pseudogroup of information, it just means that S is the restriction of T to some subset. So so it's the supremum is with respect to this order. Okay, so that was the first task.
Can you say again what fundamental means?
Yes, it means that it is a pseudogroup. It means whenever you have an inverse semigroup, it acts on the idempotence. That's called the Neumann representation. And being fundamental means that this representation is faithful.
Okay, thank you.
Okay, now I'll go the other way. So I just erased the construction of the fundamental algebra from an equivalence relation. What I'm going to do is, how do you construct a fundamental algebra? So from a twist. Now, so a twist is this data. So from a twist to a Cartan pair. So I need a commutative fundamental algebra. So I call it A. And as usual, AP are the projections of A, API are the partial isometry. So suppose that I have what I call a twist. And as above, G is fundamental, so it's G fundamental. So you see, it should satisfy these conditions. So you have to when an extension always at the level of idempotence is the identity. So all these inverse semigroups have the same state of idempotence. So which is the projections of it. So how do I build a star algebra and then a fundamental algebra from this data? So I'll do it formally and then I will make it more precise. So turn what I would call MC jar so finite sums. So UI is in N, AI is in A, into a star algebra. Okay, it's enough to know how you multiply UA and prime A prime. So you just have to put the U on the side, so that will be U prime, alpha U prime star, and that's the notation that I use of A prime. You see, alpha U acts only on the projections, but you can extend it once you have the Boolean algebra star homomorphism. You can extend it to the algebra generated. So it does mean, and you put A. And the star is just what it should be. So that's okay. That should be A star U star, but you have to put A star on the right here, so that will be alpha U of A star. Okay, but has it a meaning? And that's one difficulty. And the second difficulty, of course, you have A which sits so formally we are like this, and you also need an expectation. So I show you a nice solution. So that's not here. That's probably my only contribution. At least your original I do exactly what I did when I studied the Cartan subalgebras in C-star algebra. So you introduce D, which is a set of, first, you introduce the spectrum of A. So that A is not defined C of X. And you introduce D, which is X, U, Y in X times N times X, such that X, I use the same notation. I use alpha U for the what's called the Neumann representation, and at the level of spaces, I use phi U. That's the map induced by alpha U. So X should be the image of. So that makes sense. X, Y belongs to the domain of U, and X is phi U of Y. That's one step. I define two equivalence relations. That's the only point a little bit subtle. So I say that X, U, Y are usually equivalent to X prime prime Y prime if Y prime equal to 1, and there exist A and E prime in A, such that A of Y equal A prime of Y equal 1, and UA equal U prime. That's the first relation. I introduce a very similar relation this doesn't change. But here I only assume that the absolute value I it's the difference between partial isometry and a projection. It's not just take that. And same anyway. I set the sigma, the quotient. Now, believe me, it has an obvious structure group, so it's a group. G which is the quotient by the second degree, is also a group. But it's in fact it's a group of germs. I say that G is fundamental, so it needs a pseudo group. So it is in the germs of G acting on X. Okay, if you don't know the definition of a group of germs, that's the definition. And we have a groupoid twist. So X. So even in the sense that have been introduced by Alex Kumjian long time ago. Okay, now we are in a good shape to define a star algebra and a representation. And so you can identify or what I call the CC of GC now. So I just it's a little so you can so UI the arm as a function on sigma. And so UA, so you have to say what, so the equivalence class of XUY, I'm writing this, XUY. Oh, yeah, I should put a V here. So that's U of X, V, Y, and A of Y. A of Y has a meaning because Y is a character of the algebra A. And I have to tell you what's U of X, V, Y is. So it's equal to theta conjugate if X, V, Y is of the form X, U, or theta U, Y. Theta is just a complex number modulus 1, and 0 otherwise. Now, okay, I'm not going to write the formulas, but we know we have a convolution product and star product in this. So we do have our star algebra. And now we need a representation, and the representation, in fact, we have an expectation E from CC into C of X. It's just a restriction. Now, the people who are familiar with Cartan subalgebras in good points know that there is a problem with this restriction. If G is not Hausdorff, it's not well defined. But with this assumption, G is Hausdorff. This comes from the fact that X is a Stonian space. So the closure of an concept is open, which is a surprising property, but not so now we have everything which is needed. So we construct L2 of E. Once that's the completion of CC of G that we view as a CX module for so the product FG we need a Hilbert space. So you take H, which is N2, you do the tensor product over A with L2. L2 of A You know, it's a standard, whenever you have a fundamental algebra, you have a standard representation. You take a weight, here you take a measure, you measure the class, and that's the usual empty space. And G or N is represented on each. It's just the regular representation. So just by left multiplication, you define this is a way. And the fundamental algebra that you want is just the weak closure. And you automatically you get A. And things that you can G. Okay, so I have to stop here because my time is up. It's not difficult here to check that these two operations are inverse of each other. But we are unfortunately, okay, that's a nice thing, but we are not finished. We haven't, we are not here. How do we get the space X is not, this X is not this space, X is much too big. Here we want standard measures. So how do you do that? If H is separable, L2 of E has a basis. There is a notion of orthonormal basis in C-star modules. So, and because of the separability assumption, this basis will be a countable basis. And it corresponds to a countable set in G. And once you have a countable family of partial transformations, then your atom is measure-theory. You just get rid of all of the null sets, and you can realize them relay on a decent space. So you get a pseudo group on a decent space, and then you can get your equivalent solution, define the equivalent solution. But you see, there is some work to from you going from this approach, inversely group. So let me start.
Great, thank you very much, Renault. Any questions?
So you said G is Hausdorff because X is a Stonian?
Yes.
Because it's the spectrum of a Zeta
It's, yeah, X is the spectrum of a fundamental algebra.
which implies it's Stonian.
Yeah.
Okay.
In fact, here that's the fact that it's hyper-Stonian because it carries measures. But here, the fact, you know, it's related to you look at the fixed points, you have one of these partial transformation phi. And the set of fixed points is a closed set. The condition is that the interior of the set of fixed points should also be closed. That's the condition, that's a general fact about groupoidal germs. Groupoidal germ usually is not Hausdorff. But if any transformations and this property that the interior of the fixed point, of course, if the action is free, there is no problem. But you look at the interior of the fixed point, then it should be closed. And in our case, since the closure of an open set is open, there is also that notion which has been pushed by inversely good people, which is the condition that as I say that the inverse semigroup is an ordered set, it's order relation, and the condition that they have is that it is an if semilattice. So whenever you have two elements, they have upper lower. We have an if. And that's the condition really for the nuclear germs to be observed.
And I guess that follows from the fact that it's complete, right? So you have two elements and you can look at all the things below those two elements.
Yes.
They have to have a suit, so that means those guys have.
That's that should be much nicer to have a direct proof, yes, without going, yeah, that's right.
Any other questions? Well, yeah, I guess maybe I have a question. I mean, we were sort of discussing this before, but so this is all based on the fact that you start with an abelian polynomial algebra, and you already know from classical theory that with an abelian polynomial algebra arises as L infinity of some measure space.
That's true, yeah.
So that already gives you the unit space at least of your group of.
Yes, but here I'm using, I am viewing this algebra as a simple algebra.
Right, so this is a different space, but then you at the end, you know, you can,
Yes.
you can then somehow.
Yes.
But you were saying, but the difficulty you were saying is that it's not clear how to directly construct this measure space just from the Stonian space you get from the Gelman spectrum.
Yes, you see, I would say decomposition of fundamental algebra. So an abelian is something technical. It's well done, but the indication is. But all these decompositions always rely about picking inside your fundamental algebra a separable and C-star algebra. But you cannot avoid that. And you say, there's something that you may have encountered. It's Takizaki equivalence relation.
Yeah.
Because it's a way of also obtaining this equivalence relation. But the Takizaki equivalence relation also relies on the fact that you will pick inside your fundamental algebra a separable which is the
There's no way you could out of it. Because
no, it's
inverse subsidy group and there's on there. Not really.
no. You see, okay, what the difference between what they spend a lot of time showing they want to they define the expectation very well, but the difficulty is to show that it's completely possible, so that you can do GNS construction. And yeah, that's just a little trick. You could you could. It's just a little trick to show that you have some possibility.
Thanks. What there's no questions here, no questions in the chat, and yeah, let's thank John again. Do you want to introduce next week, Karen?
We don't have a title or anything yet, actually.
All right, let's get it going.
Yeah.
So next week we'll have on something to be announced. So hopefully that.